Hi guys, welcome back to Math TV with Professor V. In this video, we're going to cover Chapter 10, which deals with inferences for two population means. And to start off, we're going to look at Section 10.2, inferences for two population means using independent samples. Standard deviations are assumed equal. So what the idea is in this section is we want to compare the means of two populations based on independent samples. If you'll remember from when we studied probability, right? If we have two different independent samples, it means that selecting one member to belong to a sample does not affect the probability of another member being selected in the other sample, or even in that sample too. So in this section, we're going to study a particular kind of test called the pooled t-test. And then in the next section, we're going to look at a non-pooled t-test. So the big difference between deciding which one to use is this assumption right here, whether or not the standard deviations are assumed equal. Okay, there's four main assumptions, so let's go through them. First one is that each of the samples is a simple random sample. I mean, that's pretty run-of-the-mill, right? We always just have to have that assumption satisfied. Second one is that these are independent samples. Okay, so we're comparing the means of two populations, and the sample representing each population, these two samples have to be independently selected. We will look at dependent ones coming up. So this one's one you need to pay attention to. 3, normal populations or large samples. And then 4, we're assuming that we have equal population standard deviations. And what happens when we make this assumption is we pool the data to compute a pooled sample standard deviation. We won't be doing any of that by hand, but that's what's going on behind the scenes. So that's why it's important that you only choose to use a pooled t-test when you can make the assumption that the population standard deviations are equal. Now notice, say you have sample 1, sample 2, basically you're assuming that sigma 1 equals sigma 2, but we don't have sigma 1 and sigma 2. We're using a t-test anyways. So we're going to be finding a pooled sample standard deviation. I'll show you exactly what that's going to look like in a little bit. But basically, this assumption means we use the pooled t-test. Okay? Now, when we're setting up a hypothesis test and we're comparing two means, the null and the alternative look a little bit different because obviously now we have a mu1 and we have a mu2. And there's two main ways that we write out our hypotheses. So I'll show you both because some textbooks use one way and then StatCrunch does it a different way too. So it's just good to understand your options. So if you have a right-tailed test, the null is the same for all of these guys, right? Mu1 equals mu2. That's going to be the same for left-tailed and for two-tailed. That's always the same. Alternative, I'll put H1. For a right-tailed test, we would have mu1 is greater than mu2. For left-tailed, we would have mu1 is less than mu2. And then two-tailed, can you guess? Mu1 does not equal mu2. Good. Now, another way that you'll see this written out basically is the rearranging and moving mu2 over to the other side of the equation or inequality. So, or another way that you would see the null is written as mu1 minus mu2 equals 0. And then the alternative would be mu1 minus mu2 is greater than 0. Okay? And then same thing for the others. So you would do for the null, that's the same. Mu1 minus mu2 is 0. And then this time the alternative would be mu1 minus mu2 is less than 0. And third case for a two-tailed test, the null would be mu1 minus mu2 equals 0. And then alternative mu1 minus mu2 is not equal to 0, like that. Okay, so if you're going to perform a pooled t-test, then obviously you're going to need to compute a test value. And here's the formula in order to do so. So you would have x1 bar minus x2 bar. These are each of your sample means, minus mu1 minus mu2. In every single null hypothesis, this is assumed to be 0, so that you would just put a 0 in there. And then S sub p, that's your pooled standard deviation from the sample. And then you would have square root of 1 over n1, that's the size of sample 1, plus 1 over n2, size of sample 2. And this has the t-distribution with degrees of freedom n1 plus n2 minus 2. Like I said, though, we won't be computing this by hand because we'll just be using StatCrunch to help us, okay? But that's how you would find your test statistic value to compare to your critical value. And then the other kind of inference that we can perform is constructing a confidence interval. And so the process is pretty much the same assumption, simple random sample, independent samples, normal populations or large samples, and equal population standard deviation. So we assume sigma 1 equals sigma 2. Not that we have them though. And then again, we won't be using tables, but you could just find your critical value and then construct your confidence interval and interpret the confidence interval. And this is exact for normal populations and is approximately correct for large samples from non-normal populations. So anyways, let's just get into some examples right now in StatCrunch so you can see how to set these up. It won't be too tricky. You'll be fine. All right, so let's start off with question 9. Most of the homework exercises will have you use a pooled t-test, and it will tell you in the directions directly. This one I just wanted to do with you guys because it doesn't specifically tell you to, but we will again use a pooled t-test. So researchers from a certain country were interested in how characteristics of the spleen of residents in their tropical environment compare to those found elsewhere in the world. The researchers randomly sampled 88 males and 112 females in their country. The mean and standard deviation of the spleen lengths for males were 11.2 centimeters and 0.8 centimeters respectively, and those for females were 10.1 centimeters and 0.9 centimeters respectively. At the 1% significance level, do the data provide sufficient evidence to conclude that a difference exists in the mean spleen lengths of males and females in the country? So just to start off, let's figure out what the null and alternative hypotheses should be. And they're telling us let population 1 be all males in the country and let population 2 be all females. So null hypothesis always should have an equal sign. So, you know, they're giving us this weird garbage over here. Don't even look at it. We're looking where mu1 equals mu2. And then the alternative would be just that there's a difference between the two so that they're not equal. So I'm going with B. Great. Now compute the test statistic. So here is where it's a little tricky. They didn't directly tell us to use a pooled t-test, but since, look at these sample standard deviations, 0.8 and 0.9, they're fairly close to each other. So we're going to make the assumption that the population standard deviations are equal. I know it's a little bit bold of an assumption, but anyways, that's what you need to do to get the problem right. So let's do it. We're going to go into StatCrunch now. And what you want to do is open up a t-test. Let me make this a little smaller so I can see both windows. So stat, t-stats, and this is a 2 sample. We don't have data, we have the summary. We have the means and the, oh, come on now, 2 sample with summary. Great. So sample mean for sample 1, that was the males, that's 11.2 centimeters. Sample standard deviation was 0.8 centimeters. And the sample size, how many males were there? 88. Sample 2, the mean is 10.1 centimeters. Sample standard deviation, 0.9 centimeters. Sample size, 112. We will pool the variances, okay? Because 0.9 and 0.8 are pretty close to each other, we're going to make the assumption that the population standard deviations are equal. And we're doing a hypothesis test. mu1 minus mu2 is 0. That's the correct alternative. So everything looks great. Let's compute it. Wow, what a test statistic, 9.005. They actually only want you to round to 2 decimal places, so that'll be 9.01. Ooh, nice work. Okay, I always get a little nervous. Determine the p-value. Notice we're rounding to 3 decimal places and the p-value is less than 0.0001. If you round that to 3 decimal places, it's just 0. I feel weird, but that's what, that's the right answer. So just, round accordingly. And then let's make our conclusion. So the p-value, it's basically 0. Obviously, that's going to be less than or equal to alpha, equal to or less. What do? Small p-value, smaller than alpha, reject the null. Conclude that the data provide sufficient evidence that a difference exists in the mean number of species in the 2 regions. Well done. Okay, next question. Question 10. Here it's a little more straightforward. It says preliminary data analyses indicate that you can reasonably consider the assumptions for using pooled T procedures satisfied. Independent random samples of released prisoners in the fraud and firearms offense categories yielded the following information on time served in months, obtained this time a 95% confidence interval for the difference between the mean time served by prisoners in the fraud and firearm offense categories. So they give us the data, but notice we can't export it to StatCrunch. Obnoxious, but not a problem because they gave us all the means and standard deviations. So we didn't really need the raw data here. The only purpose of seeing it is so I know the sample size for each. 1, 2, 3, 4, 5. So there's 10 in each of these 2 samples. And again, we're doing pooled T procedure since they told us to. So T stats, this is 2 sample. This time we're going to go with summary. Okay. So sample 1, sample mean, just enter everything there, 10.94. Sample 1 standard deviation, 3.85. And the size, because I went through and counted how many there were, was 10. Sample 2, mean is 19.52. Sample standard deviation, 5.02. Sample size, again, 10. Pool these variances. I don't think there is anything non-pooled in the homework. So sorry, don't be mad. And then confidence interval, 95%. Oh, it's already there. Compute, please. And this time we're rounding to 3 decimal places. Okay, so lower limit negative 12.783 to negative 4.377. Nice work. Okay, next question, one more, just because this is a little bit of a different idea. The following relationship holds between hypothesis tests and confidence intervals. For a 2-tailed hypothesis test at the significance level alpha, the null, that mu1 equals mu2, will be rejected in favor of the alternative if and only if the confidence interval does not contain 0. So basically, reject the null if the confidence interval doesn't contain 0. In each of the following cases, illustrate the preceding relationship by comparing the results of the hypothesis test and confidence interval. And it has to be for a 2-tailed, right, hypothesis test. So here, look, they're telling, here's my null, alpha's at 0.05, here's the p-value. The confidence interval for the difference in last year's mean household vehicle miles of, all of this is irrelevant. I'm just going to look at the confidence interval, negative 4.92 to 1.77. Does that contain 0? Yes, it does. And remember, this statement here, the relationship tells us that we reject the null if and only if the confidence interval does not contain 0. So what that means is if it does contain 0, you fail to reject the null. So that's what's going to happen here for A. We do not reject the null because the confidence interval does contain 0. Okay. And then that means if we're not rejecting the null, there is not a meaningful difference in last year's mean household vehicle miles of travel between Midwestern and Southern households. The relationship holds. Okay, let's check that answer. Fantastic. Now, example B. So we're not doing anything in StatCrunch. They basically gave it all to us. So same null, alpha's 0.05, p-value. I'm not even looking at that. I don't even care what they're talking about, these spleen lengths. No, I'm looking right here at these numbers for the confidence interval. Negative 2.596 to negative 0.004. Those are both negative. So that means 0 is not contained in that interval. And what did the problem tell us in the beginning? The relationship is that in this case, we would reject the null because the confidence interval does not contain 0. Okay, there is a meaningful difference this time, and the relationship holds. Always pick holds. Okay, so that's it. I thought that was a little bit of a funky one that we didn't really talk about in the lecture previously, so I wanted you to see how to do it. All right, so now let's jump into section 10.3, inferences for two population means using independent samples. Only difference is now standard deviations are not assumed to be equal. So if we remove the assumption that the standard deviations of our two populations are equal, then we use a non-pooled t-test to compare two population means. So notice here, the only difference when you're computing the test statistic is right here. We don't have that SP, that pooled sample standard deviation. We have sample standard deviation 1 and sample standard deviation 2, okay? Again, don't worry about computing the test statistic by hand, but here's basically the assumptions. We have to have simple random samples, okay, no surprise there, independent samples, and then lastly, normal populations or large samples. So we just removed assumption 4 that the population standard deviations are assumed equal. So when that's gone, you're going to select a non-pooled t-test. That's the big thing to keep in mind. And then null hypothesis is always the same, and the 3 alternatives are the same as before. So nothing has changed here, okay? So non-equal standard deviations of the population, non-pooled test, t-test. And then same thing, you can set up a confidence interval. Don't get bogged down by all the formulas. I just wanted you to have all the steps listed out. But again, we're just going to get into StatCrunch. Don't even, put the formulas on your note card or anything. You won't need them. The biggest thing I want you guys to take away from this is, how do you know when to use a pooled versus a non-pooled T procedure, either for a confidence interval or for a hypothesis test? Because say you end up going into research or you need to set up a study, which one should you use? Well, basically, if for some reason, when you're looking at the two populations in question, if you're reasonably sure, okay, so what's reasonable? I know, right? That allows for some interpretation. If you're reasonably sure that the populations have nearly equal standard deviations, then use a pooled T procedure. But if you're not reasonably sure, then just use the non-pooled, okay? All right, last section for chapter 10 covers inferences for two population means using paired samples. So here, what we're going to do is look at a test involving dependent samples. So this is different than what we did in 10.2 and 10.3, where we required independent samples. So why do we want dependent samples? Well, this means that the subjects in the two samples are matched or paired in some way. That's relevant for our study. We want this. When the two samples are dependent, we use the t-test for dependent samples that measures the differences. So you're going to be subtracting in the matched pairs of values. So for example, if you wanted to study like before and after effect, or something where you want the two samples to be correlated or paired up in some way. Okay, and the test value formula again follows the basic format of observed value minus expected value divided by your standard deviation. And the test value formula for the t-test for the difference of two means is as follows. So t equals d bar minus mu sub d divided by S sub d over rad n. So what is everything there? Well, mu sub d, that's the differenced mean, that equals mu1 minus mu2. So basically we have these two population means and we're subtracting them. We're finding their difference, and that gives us mu sub d. And to find d, you take your two samples and we'll call them x1, x2, and you will subtract or find the difference between each of the pairs. From there, once you have d, then you're gonna compute that sample mean and standard deviation, okay? And you can do that, using technology. We're going to be using StatCrunch. They give you the formula for computing the sample standard deviation of those differences, but we don't need to do that. Degrees of freedom are n-1. All right, now forms of hypotheses for comparing the two means. Remember, mu sub d, that's the symbol for the expected mean of the differences of the matched pairs. So your textbook still uses mu1 minus mu2. A lot of textbooks or studies instead will just use mu sub d because it's cleaner. And I'm sure for other reasons. So h naught, mu sub d is 0. Alternative would be mu sub d is greater than 0. Left-tailed, can you guess? Still mu sub d equals 0. We're always having the same null, okay? And then alternative is that mu sub d is less than 0. And then two-tailed, mu sub d equals 0. Alternative, mu sub d does not equal 0. What your book likes to use is still what we did in 10.2 and 10.3. So they'll just put mu1 minus mu2 equals 0. Mu1 minus mu2 is greater than 0, etc. It means the same thing, okay? It's just cleaner, I think, if you use mu sub d. All right, and then for all of the examples we're going to cover, assume the variables are normally or approximately normally distributed. Now, if you take a peek up here, this test value isn't too hard to compute by hand, so I do want to do one example so you can see kind of how everything's going to work, and we'll just do a traditional method hypothesis test right here. So example 1, to test the effect of a physical fitness course on one's ability, the number of sit-ups that a person could do in 1 minute, both before and after the course was recorded. 10 randomly selected participants, so there's our simple random sample, scored as shown in the following table. Did a significant amount of improvement take place? Use the 0.01 level of significance. So notice our sample size is going to be 10 because we have 10 participants. These people were randomly selected, but these two samples of their number of sit-ups before and after the course are definitely dependent because this is participant 1, right? This is participant 2. So everything's matched or paired. So in a before and after study, you definitely want to use this dependent or matched t-test. Okay, so first we need to compute D, all of the differences, right, between each of the data values here that are paired. So D, and remember our formula is x1 minus x2. So we got to decide which one's x1, which one's x2, and what makes more sense in your brain. So before and after, maybe you would think, oh, let's call before x1. And that would not be good because if you do x1 minus x2 and say they could do more sit-ups, then that difference would be negative, which is kind of a weird way for your brain to think about it. So I'm going to call after x1 and before x2. That way, if you do more sit-ups, then that difference will be positive, right? So notice this person could do 30 sit-ups after the course and only 22 before. Since I'm calling after x1, 30 minus 22 is 8, which means they did 8 more sit-ups. And a positive number is easier to interpret, right, in terms of improvement. Okay, let's go through and find the differences for the rest. So 26 minus 25, that's 1. 25 minus 29, oh, negative 4. See, now it makes sense. That's negative. They did fewer sit-ups after. A little weird. Okay, 35 minus 26, that's 9. 9 more. 33 minus 24, 9. 36 minus 31, 5. 32 minus 46, negative 14. What happened to them? Maybe the course was so grueling, they were just too wiped to do this physical fitness test. Okay, 54 minus 34 is 20. 50 minus 28, 22. And last one is 14. Okay, so now the only data that you're going to be looking at is right here. Don't look at the before and afters anymore. This is D, and now we need D bar, the mean, and sample standard deviation. So you could do that in StatCrunch, or if some of you know how to do it in your calculator, go for it. Like I said, I'm just doing this example for fun so you guys can see how it works. When you do StatCrunch, it'll do the whole hypothesis test for you. Okay, so D bar, I have that here. It's 7 on the dot, yeah. And then sample standard deviation, I rounded to 2 decimal places, 10.82. Okay, so state the hypotheses and identify the claim. So null hypothesis, always the same, mu sub D equals 0. Or as your homework and book like to do, mu1 minus mu2 equals 0. And then alternative is going to be that mu sub D is greater than 0. Why do I say that? Because look at the question here. Did a significant amount of improvement take place? Okay, so they're interested or claiming that the number of sit-ups went up that a person could do. We're gauging all of your physical fitness ability based on sit-ups, okay, whatever. Or so how would that be written in your homework or in this book? Mu1 minus mu2 is greater than 0. Either way, that's the claim right there. They're claiming, right, or suggesting that there's improvement. Decide on the significance level alpha. They gave it to me. It's 0.01. So that's what we're using. So alpha equals 0.01. And this test is right-tailed. Okay. Now we're going to compute the value of the test statistic. So I'll write the formula again here. So T equals D bar minus mu sub D over S sub D over rad n. And then D bar we have right there. It was 7 minus, you always assume mu sub D is 0, divided by 10.82 over rad 10. So sample size, you use how many pairs you have. It's not 20, it's just 10. And this comes out to 2.05. So that's my test statistic. Okay, step 4 asks us to find the critical value. And I wanted to show you how we used to do it with the table back in the day. So degrees of freedom are equal to n minus 1. So remember, we had 10 pairs. Minus 1 is 9, and then alpha was 0.01, right? So you bust out that student T distribution. I have a screenshot of just the piece that you would need. So here's your degrees of freedom. We go to 9 degrees of freedom. And then alpha is 0.01, so that's the area in one tail. And where do they intersect? At this value right here. So this is our critical value. I'll just round it to 2 or 3 decimal places is fine. Let's just do 2.82. So here's the idea, okay? Here's my T distribution. It's a right-tailed test. So here's the mean, 0. Here's 2.82. That's my critical value. So that separates the critical and the non-critical regions, right? This is the critical region, or the rejection region. And this is the non-critical region, non-rejection region. So now step 5 asks us to make the decision to reject or not reject the null. Well, where was my test statistic? Where did it fall? It was 2.05. So plot that on the distribution. Ooh, 2.05 is smaller, right, than my critical value, less extreme. 2.05. 2.05 falls in the non-critical region, aka non-rejection region. So that's my decision right there. Fail to reject or do not reject H naught. Okay, and then summarize the results in terms of the claim using a complete sentence. So there is not sufficient evidence to, I'm going to use the word support because the claim was in the alternative hypothesis. The claim that, what did they claim? A significant amount of improvement, yes. Took place. And I want you to kind of study this sentence a little bit because it is so telling. There is not sufficient evidence. I mean, maybe a significant amount of improvement did take place in their physical ability, but they were just measuring the number of sit-ups they could do, for crying out loud. I think you need a more robust test, right, to assess your physical ability. So the way we summarize hypothesis tests is really telling, really precise, because it's just saying that the evidence doesn't support that, but maybe the evidence you collected was not appropriate, right? So many ways to dissect things. So you guys be savvy too. When you read the results of studies, watch how they were set up, watch how things are worded, because you can make the results sound more meaningful or swayed a certain way if you have an agenda for some reason. So watch out. Anyways, moving on. So that was a hypothesis test. You can also set up a confidence interval, same procedure. We won't have to do an example by hand, but it's not too bad to do. Again, though, to get your T sub alpha over 2 value, you would need a table or StatCrunch. So let's just hop into there and look at some examples, and then that's the end of chapter 10. Okay, here is question 16. Cooling down with a cold drink before exercise in the heat is believed to help an athlete perform. A researcher explored the difference between cooling down with an ice slushy, and with cold water. 10 male participants drank a flavored ice slurry and ran on a treadmill in a controlled hot and humid environment. That sounds like torture. Days later, the same participants, it's the same participants, that's why it's paired, drank cold water and ran on a treadmill in the same hot and humid environment. The table available below shows the times in minutes it took to fatigue on the treadmill for both the ice slurry and cold water. Preliminary data analyses indicate that the use of a paired t-test is reasonable. At the 1% significance level, do the data provide sufficient evidence to conclude that on average, pay attention here, cold water is less effective than ice slurry for optimizing athletic performance in the heat? Use the p-value approach, and they gave us the mean and standard deviation of the paired differences. So you could do it with summary. I'm going to show you guys how to use it with the data. Why not? It'll be fun. Open that bad boy in StatCrunch. Okay, there it is. Let's put it over there for now. We're done. So what are the hypotheses for the t-test? Let population 1 be the times to fatigue for cold water, and then population 2 be for ice slurry. And notice here they said cold water is less effective. That's what they're claiming. So if cold water is less effective, then that would be that the time for the cold water would be less than slurry. So mu1 would be less than mu2. I mean, what is this? Do they think we're still going to pick that? No. A. We know the null has to have equality. Check. Fantastic. Okay. So here we're going to find the test statistic, and I wanted to show you guys how to use the data in StatCrunch. So go stats, t-stats, hop on over to paired. Yes, look at that. And then sample 1 is cold water. Sample 2 is ice slurry. And then hypothesis test is that mu sub d, the difference would be less than 0. Remember, mu sub d is mu1 minus mu2. That's pretty much it. Compute, please. So the test statistic, which we're rounding to 2 decimal places, that's t-stat. That's going to be negative 5.21. Nice. And then Anything else? Find the p-value, 0.0003. But if I only round to 3 decimal places, then it's 0.000. Okay. So let's summarize. P-value way less than alpha. It's basically 0. So that means we reject the null. The data provide sufficient evidence at the 1% significance level that the effectiveness of cold water for optimizing athletic performance is less than that for ice slurry. Well done. Okay, last example here. Question 17, this is for a confidence interval. It says, a scientist investigated the effect of cross-fertilization on the heights of plants. In one study, the scientist planted 15 pairs of a species of plant. Each pair consisted of one cross-fertilized plant and one self-fertilized plant. The table available below gives the height differences in eighths of an inch for the 15 pairs. Each difference is obtained by subtracting the heights of self-fertilized from cross-fertilized. Use the paired t-interval procedure and determine a 95% confidence interval for the difference between the mean heights of cross-fertilized and self-fertilized. And you can open the data, or let's use summary stats this time. And they told me what the mean is for the differences and the standard deviation. So if I'm going to use the summary, then I don't need to click paired data because the differences have already been computed for me. So you're just going to go to t-stats, actually pick one sample, since subtracting all of the paired data creates one sample of differences. Does that make sense? So go to with summary, one sample. Sample mean, just put what D bar was. So that's 19.73. Sample standard deviation, 36.85. Sample size, they told me there were 15 pairs. Okay. And we're doing a confidence interval this time at the 95% level. So compute, please. And we're rounding to 2 decimal places. So this lower limit would be negative 0.6. I got to round that up to 8. And then upper limit 40.14. Nice. Okay. And then which statement below best interprets the confidence interval? 95% confidence that a pair has that difference? No. Remember, this is a difference in the means. Means. Let's see. Difference between the heights? No. Difference between. Here we go. There's a 95% confidence that the difference between the mean heights, look for that word mean, yeah, of cross-fertilized plants and self-fertilized plants is in the interval. That's the one. Check it. We're so good. Okay. So that's it. You guys should be able to get through the homework. Like I said, most of the t-tests earlier are pooled instead of non-pooled. And for the paired data, you can either use the data or use the summary. It's up to you. Hope you guys found this helpful. Give the video a thumbs up if you liked it. Subscribe, Math TV with Professor V, if you haven't already. And stay tuned. We've got more great statistics coming your way.